Okay, so today we'll be explaining an AP Physics free response question. So here is our situation. Here's our situation. See, there is a ramp, a curved ramp, where the radius of curvature is 50 meters. This car here weighs 2,510 kilograms. The angle of the ramp is 30 degrees, and there's friction between the ramp and the car, and the coefficient of static friction is 0.43. Now, we are asked to find the max velocity in which the car does not slide up the ramp. Right? Okay, so how do we go about that? Well, first, it's like solving any physics FRQ. It's best if we draw out our free body diagram. Now, let's go over the forces that are on this car. First, we have the force of gravity, which always points straight down. So there that is. And then opposing gravity, we have normal force. Now, what is normal force? Well, let's go over that real quick with more paper. Okay, so Newton's third law states that every action must have an equal and opposite reaction. Because gravity is always pulling down on you, there must be a force that is also pushing up to make sure you don't, just fall through the ground or whatever. So that force is the normal force. It is the force that is opposite and equal to gravity. So as we can see here, gravity down, straight down, normal force straight up. And because of this, so we know that we can say that force of gravity is equal to your mass times the acceleration of gravity, when acceleration of gravity is equal to about 9.8 meters per second squared. So if we know it has to be opposite and equal, then we know that the normal force is also equal to the force of gravity, which is equal to mg. So that's the normal force that is acting on this car. An important thing to note, however, is that we are on a slant here. We're on a slant. Therefore, this normal force cannot point straight down. I actually drew this wrong. Hold on. It does not point, it does not point straight up, as I drew incorrectly. Instead, it points like perpendicular to the surface. So it's really like that here. And because we're on a slant, we have to split the normal force into components using some trigonometry. So we can say that if this is the normal force, then this component here would be F normal force cosine theta, and this here would be normal force sine theta. So that's how we split that up, so that we're still perpendicular, or we're still opposing gravity. Okay, the next force we have to draw, we have to add on is friction. Now we know this as friction, and friction is working opposing here, right? So it's working to stop the car, or to keep the car in going around a circle. So friction vector is over here, noted by this F. This curvy F is friction. I just wrote the whole word. But so friction is equal to the normal force, which we talked about earlier, which is just mg, times the coefficient of static friction. So friction is equal to normal force times coefficient of static friction here. But we can also say that the friction is actually equal, because we know that normal force is equal to mg. Friction is equal to mg times the coefficient of static friction, denoted by this mu s here. Okay, so just like the normal force, gotta split that up into components too. Okay, how are we gonna do that? Well, what we have to do is similar to the normal force. We split it up using trigonometry. So we get that the friction in the horizontal direction is F cosine theta, and in the downward direction it's F sine theta. So now this has been split up into the force of friction has been split up into F cosine and F sine. Okay, so now we know all of our forces that are acting on this car. What do we do with that? Well, first off, we know, let's sum these forces. That's what we have to do. So the force of gravity, because we know that if we don't want to slide up the hill, everything has to stay constant, right? There's no changing in acceleration or anything like that. So we have to sum the forces and make sure that that whatever velocity we have sums these forces correctly. How do we do that? Let's start with our vertical components. So we have gravity, force of gravity, mg, and that is the other force you're adding is the force of friction times sine theta. Now we know our theta is 30 degrees, and those two forces together are equal to the normal force vertically, which is normal force times cosine theta. Now it's good to isolate our normal force. So we got to do that. Sorry, brain fart, but we're back. So to solve for our normal force here, what we're going to do is we're going to turn our friction into our other form here, which is the normal force times the coefficient of friction. So let's do that. Let's rewrite this equation. mg plus f. Okay, so now that we have this equation, we can do some rearranging and dividing and some other stuff, and we can isolate our normal force. And when we do that, we will get that our normal force is equal to mg over cosine theta minus mu s sine theta. Wonderful. So that's our vertical components balanced out, and now we have something we can substitute in for our normal force, which is great because now we have to move on to our horizontal forces. I think I'm gonna need more room. Yeah. All right, let's do it. So, horizontal forces. We have three forces that we need to do. So we have our, let's use our diagram here. We have our normal force, sine theta, going this way. We have our friction times cosine theta going this way. And then so those two cancel out. So we have theta. But then we have one more force that we have not accounted for yet, and that is the centripetal force. Because we are going around around a curve, that is the force that is keeping our car from sliding up this ramp. That's the velocity, and that will contain the velocity that we're looking to solve for. So how do we, what is centripetal force? How do we solve it? Centripetal force is the force that keeps an object moving in a circular path, essentially. So if we had a circle, and something was going around this circle, it's the force that keeps it from, instead of shooting out this way, it was coming around without any centripetal force, it would just continue to go this way. But the centripetal force keeps it towards the center, keeps it going around in a circle. And that equation, well, okay, Newton's second law states that F is equal to ma. And we know that centripetal acceleration, AC, is equal to velocity squared over radius. And now, to get our centripetal force, we just substitute this into here, and we get mv squared over r as our centripetal force. So now we can come over here, plug this in right here. There's our new equation. Wonderful. So now we're close, but we're not done yet, actually. Now what we have to do, again, we're going to convert this friction into our into the other form with the normal force and the coefficient of static friction. So now we're going to have that. Bang. But what's our normal? So now we have mostly variables we know. We want to solve for our velocity. We know everything else. We don't know our velocity. We don't know what this normal force is. Lucky for us, we solve for our normal force in things that we do know before with the vertical components. So let's go ahead and plug that in. First, we'll make it easier. We'll factor out the normal force of both of these, and then we're going to plug it in. So it'll look like this. Okay, this is our final equation. We know. Now let's go back, or I'll write it out again. Those are the variables we're given. They're all in this equation. We just got to plug it in and isolate our v over here. And when we do that, our hold on. Sorry, I forgot how to do algebra. When we do that, when we isolate v, we'll get that v is equal to the square root of r times g times sine theta minus mu s cosine theta over cosine theta minus. And when we got input, we know all of these things that were given to us in the problem. When we put them in and solve, we get that v is equal to approximately 31.1 meters per second. Thank you.